Okay, hi everybody. So I'm Nicolai Shapiro. I will start with some introduction to the school. And I start with what Angelique already shown. We are at this Institut d'études scientifiques, and there is a team who manages this institute who really helps to organize this meeting. So I think we all need to recognize and acknowledge their contributions to this. And then this is our school, and it was organized by these two committees, scientific committees. Some people are here, like Marine Denol, Céline Michel, and Greg Beroza will arrive. And then here we are, organizing committee. You will meet all us, and I think you already could see that the main organizing person was Laurent. Thank you, Laurent. So, okay. So now let's start with some scientific introduction. Okay, before we start with scientific introduction, I think you all have seen this program online, but there were some last-minute changes, hopefully really last, but we will see. So there was a change of presentation, this one, so because Ludovic Margerin could not come, and so we replaced his presentation by larger presentation from Alexandre Aubry, and then there will be a presentation on planetary seismology by Sabrina Menina, okay? And then another change was again, Léonard Seydoux could not come, and this will be Reza Esfahani who will do this presentation. Did I forget something? Laurent, no? It's okay? So it was already modified online or not? Okay, good. So, no, what we have here. Okay, and these are the poster sessions. Posters will be placed just there. And because there are many posters, everything was divided in these two sessions. I think Laurent sent the email, so I hope everybody knows in which group his poster is. Yeah. And basically, there will be introduction to posters tomorrow and on Wednesday. Okay, with these one slides that you hopefully sent. Yeah, I think the idea will be that with this one slide, everybody presents himself, but we need really to make this quick, maximum 30 seconds. What was? Okay. It's better to discuss outside close to the posters. Okay, by the way, the weather is expected to be nice all the week, so this will be perfect for poster sessions. Okay, I think it's all about the program. Okay, so this is our school, and this is just a copy of its announcement from the web page. And I just start with emphasizing some keywords like wave propagation, complex media, seismology, and all this different stuff. So this is what we will speak about this week: imaging, monitoring, detection, and then we will not speak only about seismology, but about some other neighbor disciplines. And so there will be some presentations about novel data analysis methods. And then what is also interesting there will be things about seismic hazards, new networks, sensors, many applications. And just interesting to mention, this is actually seventh school of this series. The first one was organized in 2009. And I think we should thank Michel Campillo, who actually is the origin of all this. Okay, so thank. Okay. So how this works? So first thing I start with is a few words about wave physics. So because this is the main, I think, physics subject of this, I hope this will work. Okay, so waves, this is the simple image of waves we can get. Water surface, we put a stone there and we have this wavefront. Okay, so waves basically are propagating oscillations, okay? And in simplest mathematical way to describe it is this wave equation, very famous scalar wave equation. Okay, and it's simplest and most intuitive solution for things like this is what is called spherical wave. So it's basically point source, and then the waves propagating from this point source is described by this kind of function that is an exact solution of this equation. Okay, so this is, I think, the way how we think intuitively about waves in many cases. And then what is interesting with this spherical wave, if we're far from the source, this spherical wavefront can be approximated by a plane. So we can consider locally often spherical wave or whatever wave we use as a plane wave. Okay, yeah, so this is a plane wave. Did I write the equation for it? I forgot to put an equation, but okay, you all remember the equation of a plane wave. It's a cosine or exponential function. And again, what is nice with this is an exact solution of this wave equation, so this plane wave. Okay, and it's also it's described either by cosine or sine function or exponential, and so this is has very nice properties, and it's a basis for Fourier decomposition of our wave fields. So this is why it's so often used in all mathematical analysis we do. And so it, okay, so you see it has this harmonic behavior in time or space, and this is based on this particular solution of wave equation. We define all quantities that we discuss when we speak about waves, like frequency, period, wavelengths, wave number, wave speed. Okay, so I think these words will appear many times in our talks, so I hope everybody is familiar with this. Okay, so this is about some very basic solutions of wave equations that are actually like cornerstones of all mathematical analysis we have. But so then, if we speak about real waves and real media, so we can see some of them actually when we look from here on the water. Obviously, in real media, waves are more complex. For example, these are the waves on the water. We see one wave traveling in this direction and then reflecting wave, so we have wave reflections. So if we have some media with changing properties, we have what we call refraction. Okay, you see the speed of propagation and the direction of wavefront propagation change. Okay, and then in more general situation, when wave encounters some heterogeneity or obstacle, we have what is called diffraction, that is governed by Huygens-Fresnel principle. Basically, every heterogeneity generates new waves. Okay, so I show this just to explain that even if we often operate the simple mathematical objects like plane wave, the real wave fields that we have in our natural systems, they are very complex. They are always combined of direct waves coming from our sources, reflected, refracted, diffracted waves. Okay, and this is what we deal with. Okay, now after these few general words about waves, let's speak about more exact subject of this school. We will speak here about waves in the S, in broad sense. Okay, and most, I think, famous or well-known topic here, it's seismic waves in the S interior. So it's a subject of seismology, and seismology is, again, one of the main topics of this school. I think like 80% of presentations will deal with seismology. Okay, and you maybe all have seen this figure when we have seismograms that correspond to waves propagating through the S. So this is one big part of the school what we will speak about. But then there are seismic waves in other planetary bodies and other planets, and recently there was this very famous project SEIS InSight, when seismometers was sent to Mars, and many, I don't know how many, a few years of data were recorded with different events. So this was a big advancement for planetary seismology, and we will have one presentation. I think it's tomorrow by Sabrina Menina. Okay, so we will speak about not only S seismology but also planetary seismology. Okay, then if we speak about the S, again, the waves are not only inside the solid S. we have the waves everywhere. For example, if we look from the beach, we will see the waves in the ocean. And actually, there are many different types of, of the waves in the ocean. Surface wave, internal waves, gravity waves, okay, many things. And there will be presentation, hopefully he will arrive on time, by Fabrice Ardouin. Okay, he will speak about physics of these waves. Okay, another example. Okay, so this is satellite image taken after, or a compilation of images taken after the big eruption of Hunga Tonga volcano in 2022. Yeah, thank you. And so this you can see, the eruption was here, and you see this wavefront. It's actually strong pressure wave propagating in the atmosphere. So there are a lot of waves in the atmosphere, and we will have presentation by Matt Haney about these waves, maybe not at this scale, and about the field that is today called infrasound monitoring. Okay. So, and then maybe a very important thing to mention about all these different types inside and outside the solid S, they are all are coupled. So basically we have this system as shown here, where we have the solid S, ocean on top of it, atmosphere, and if we have some perturbation, for example, within the solid S, it will affect the atmosphere, generate atmospheric waves, and then the same with the ocean, and also, for example, the oceanic waves couple some situations very well with the solid S, and this is in this way how they generate microseismic noise. Actually, the signal, I think we all now use for many things we will discuss here. So this coupling is very interesting, and I hope it will be discussed in more details in some presentations. Okay. So, but to understand waves, even natural waves that we all want to study here, just using our natural observations often is not sufficient, because with natural system we cannot explore all possible configurations, and we don't control what we study, and we don't know what really occurs, for example, inside the S. We can only make some inferences. So to better understand the physics of waves in different media, we want also to do experiments when we create configurations, controlled configurations in which we can study some particular physical effects. So this is why seismology and other wave disciplines always benefited from collaborations with laboratory disciplines, like in particular laboratory acoustics, and there will be 2 presentations about this by Alexandre Aubry this afternoon, and then by Casper Van Wyk. Okay, so we will see. They will show us so how we can relate laboratory results with our natural observations. Now let's go back to seismology. I'm seismologist. From now I will speak mostly about seismic waves, okay? And I will just give some introduction of basic things about seismic waves. Okay, seismology is defined broadly as a scientific discipline studying the generation of propagation of elastic waves in the S. Okay, so, and traditionally, from the beginning of seismology, it has been very well established that seismic waves are mostly generated by large earthquakes occurring on large seismogenic faults. And then these waves propagates through the whole S, and they can be used or have been used to actually study and establish the S structure. Okay, so traditionally seismology has been for many decades a discipline mostly about earthquakes and relatively large scale S structure. Okay, so, and we still work a lot on this subject because they are important both for basic physical understanding, but also for things like mitigation of hazards and so on. But in addition to this, seismology is more and more used for other goals, to study structures and processes in different scales in different environments. Okay, tectonic, volcanic, glacial, fluvial, oceanic, atmospheric, and also we start to be interested more and more in understanding signals related to human activities. And so this is why these days there are a lot of different applications in seismology, and this is, we will partially see this at this school. So we will still speak about the deep earth structure with presentation from Ann Paul and Robert. Yeah. So I'm sorry. So then there will be presentation about seismic faults. I don't see Huda, but he will come. Things about seismic hazard, and a lot of presentations about monitoring, general presentation about monitoring of the crust, something about volcano monitoring from Matt Haney. Then there will be presentations about monitoring and studying glaciers, partially from Florent Gimbert and Frédéric Moreau. Then something about monitoring rivers and flooding, again from Florent. Some applications to use things for geothermal energy, Arno Berman. Hydrological monitoring from Sijuan Mao, and monitoring in human environment from Laura Ermet. Laura Ermet, sorry. Sorry, Laura. Okay, so so in this slide I tried to represent, or in this next slide, the wealth of tools and information that we have in modern seismology. So basically, since a couple of decades, we use not only classical seismographs, but many other types of instruments that really allows us to make significant advancements. For example, this nodal instrument that can be installed easily in big numbers, like hundreds and thousands. And I think Florent Branguet will talk about this a little bit. Then infrasound instruments, microbarometers, and other type of sensors. And Matt Haney again will speak about this. There is this new field of rotational seismology, and Celine will speak about this. And then there will be presentations on this new, very exciting field of fiber optic sensors, DAS or others, we will see. Okay, and so with all these new sensors, we're also now, instead of sparse networks as we operated for many decades before this century, now we have many dense networks at different scales. For example, this is a famous Long Beach experiment in LA, Los Angeles, California, with more than 2,000 nodal instruments. This is the most recent ongoing experiment in Europe, AGRA. I don't know, there are also about 1,000 of sensors. Yeah, so very dense at this scale. So, and what is also exciting with all these things, that our community was successful in building this data distribution system with many data centers that are all connected via very efficient and transparent tools like web services these days. And this is just shows the configuration of this system in Europe through so-known European Integrated Data Archive. So this is a really great possibility for us to do our research. And so with all this, we have this issue of growing data. Okay, so like in many scientific disciplines in seismology, we are speaking about big data. You see in how much? 25 years, the data volumes increased by more than 2 orders of magnitude. And this is obviously very good, and especially when in parallel with this we have access to increasing computer power to process all this. But these are also challenges, because analyzing one seismogram is not the same thing as analyzing millions of seismograms. So this is why we need building new advanced data analysis methods. And one very promising direction is machine learning or artificial intelligence, and there will be 2 talks about this by Greg Beroza, who will still arrive, and then by Reza Esfahani. Okay. And then what is also very useful these days, that in seismology we have more and more well-designed, openly available software. I just put here some examples of data analysis and simulation software, but I think there are much more tools now available. And so this is, again, this is great, because I think it's possible to build, with using these things, very efficient workflows for analysis and modeling in just a couple of days. Okay, so we have all these tools, new instruments, new data, computers, software. So this is great. This is what makes advance our discipline. Still, to use it well, we need to have some solid theoretical and physical understanding of what we're doing. Okay, so I mean, I think these days it's really sometimes an issue because sometimes it's relatively easy to take this software, this data, to build some workflow, to get some results, and especially well-designed software will always produce some results. The problem with many of these packages, they never crash. So, but getting results out of a software package doesn't mean it's a good scientific result. We need to understand how to check it and so on. This is why we need to understand the theory, concepts, and also to actually to think about why we use it, what scientific questions we want to solve. And I think this is what we are trying to do at this school, actually to combine presentation about possible applications, but also with some talks about fundamental aspects of what we're doing. Okay, and so this is why I will make a very short review of what we're doing again in seismology from a more theoretical perspective. So seismology is a propagation of elastic waves through the S. Okay, elastic waves means that when we consider displacement, deformation, whatever in solid media, it's not anymore described by scalar variable, but it's described by vector variable. Okay, for example, displacement that has 3 components, and so we actually replace the wave equation with more complex equation that is written in this tensorial form. So this is a displacement, this is density, so this is elastic tensor, and this is sources, some forces. Okay, but again, this is the second order differential equation, but obviously much more complex than simple wave equation. And immediately, I will not go in details of solving this equation, but immediately we get implications. Instead of having one scalar waves, we have several types of waves. We have 2 types of body waves, P wave and S wave with different polarization, longitudinal and shear polarization. But also at the surface, we have new types of waves, like for example, Rayleigh waves. Okay, so our wave phenomena become much richer than simple scalar case. Okay, then if we think about okay, just forget. Now there are scientists who suggest that when dealing with this complex vector, I think we should take into account not only displacement but also rotational components. So there are propositions to use 6-component wave fields instead of simple 3-component wave fields. I think we will see this in an appropriate presentation. Okay. So now, when we think about real S, it's not a homogeneous infinite media. It's a media that has its geometry. So we know today that S is at large scale is nearly spherically symmetrical body with several well-known layers: crust, mantle, core, inner core. And so when we deal with wave propagating in this kind of structure, we need to take into account all boundaries and respective boundary conditions that lead to refraction, reflection, conversion of waves. Okay, but then another issue, when we look at the S structure at smaller scale, it's always heterogeneous. When we look at mountains, landscapes, rocks, you will never see anything homogeneous. We will always see the topography, some changes of rock properties, structures, fault, and even within the rocks you will see these grains. So when we deal with real seismic waves in the S, even we often use abstractions, mathematical abstractions corresponding to a homogeneous infinite media, the real case is like this. So we need to figure out more or less how to solve wave propagation in this kind of media. Okay, and this is why we introduce this mathematical object, Green's function. I think again this is the term that will be used many times during this school because this is a key mathematical abstraction that we I think use in many of our theories and practices. And basically the Green function is defined as a solution of this equation. Okay, not necessarily actually elastodynamic equation, can be applied to many mathematical equations, but to simplify, I consider this equation. And this is a solution in a media that we have, for example, within the S with all necessary boundary conditions for a point source, in this case for a force. Okay, so we call this, so we place the source in this position, look at the displacement in this position, and this gives us this tensorial Green's function. Okay, and it has some nice mathematical properties, in particular this reciprocity that is very practical when we deal with, for example, numerical simulation. Okay, and then we can use this Green's function to build a general solution. Okay, and this general solution is given by this representation theorem of elastodynamics. Okay, that states if we have some confined elastic body with boundaries, I mean with general structure inside, so we can write the wave field for a general distribution of sources inside and outside in form of these integrals. Okay, this is from Maki Richards' textbook. I will not go into detail. Basically what is important here, this is a general solution for general distribution of sources that is contains in these three integrals this Green function that represents the propagation of waves in our media as it is, and it represents sources, so volume sources, volume forces, that in many cases we ignore, and then surface sources in terms of tractions and displacements. Okay. So and so basically this theorem can be simplified in this form, that our wave field displacement is a convolution of a source term with the Green function. Okay, convolution here is in a broad sense because you see it's Green functions in some part appears as it is, in some parts as its partial derivative. But this is the, I think, the symbolic representation of our forward problem that we often use. Okay, and for example, this theorem can be used to describe wave field emitted by an earthquake. If we introduce, again, I don't go with this, we introduce some artificial surface here corresponding to earthquake, we can derive the moment tensor, and so then we only keep, I think, this term, and we end up with this representation when the displacement is a convolution of a Green function, in this case point-to-point Green function, with a tensor. Okay, so and then and I think this expression has been used for decades as a basis for earthquake seismology, for whatever we did before, earthquake source studies, seismic tomography. Okay, so we can do it like this. So we have our direct problem where we convolve in a general term source with Green function, and we can either do seismic tomography when we try to retrieve Green function, Green's function, and use its properties such as travel times to image the S, or we can do vice versa. We assume that we know somehow the Green function, and we try to retrieve source properties, for example, earthquake source mechanism, extended rupture, or we can use it actually for other sources of seismic waves, as we will discuss. Okay, so again, this Green's function is a key mathematical notion in all our theory and practice. So how is this? Okay, what is exactly the Green's function in the S? Okay, again, we have this spherically symmetrical large-scale structure with small-scale heterogeneity within. Okay, obviously we can try to develop some theoretical tool to compute waves within this structure, but actually I think it's very important to be aware that even we have today many very powerful tools to generate synthetic seismograms, they are only approximations. Okay, if we want to represent green functions at all scales, frequencies, we will not be able to do it with synthetic seismograms. Okay, so I think the real way to understand the real green function in the S is to look at the data empirically. Okay, and for this we can again use this expression that shows us that the record from an earthquake, it's a convolution of actually not Green's function, but it's special derivatives with some tensor, but again it's a point-to-point representation. So basically a record of an earthquake, it's something that is very close to a Green function. I mean, apart this derivative and this tensorial convolution. So let's look how earthquake records look. Okay, and here's an example. So this is a large earthquake occurred in Haiti, 2000. No, maybe it's not. Maybe it was 2010. I'm sorry. Recorded in Luxembourg, somewhere in Europe. Okay, and here we see very complex signal. Okay, obviously here we have some noise. Earthquake green function starts here. Okay, and if we look at these seismograms, so there are three components, I think vertical and two horizontals. We can see that there are like two parts of them. First part is composed of these waves that can be distinguished, P, S, surface waves. And then we have this decaying part that we call coda of seismograms. Okay, and obviously the properties of different parts are different. For example, for this first part that we call ballistic waves, they can be actually very well explained well with waves for which we can well define their propagation passes or properties. So direct P waves, some converted waves, direct S waves, Rayleigh waves, and so on. So this part can be mathematically described as a superposition of surface wave and directed, reflected, reflected, converted body waves. Okay, so it's obviously very, if you look at the equations, it's very complex, but it's deterministic, and it works actually quite well. Okay, and we can do this today very efficiently for spherically symmetrical S, but also with slightly laterally heterogeneous S. Now let's speak about the coda. That is maybe most interesting part for our school. First of all, let's look at coda at very long periods. Okay, for this I took a record of this Okhotsk Sea earthquake, deep earthquake, and so it somewhere in France, in Massif Central, and here is the record. I think it's band passed, so low passed at 0.05 hertz. Okay, and you can see we see this coda really decaying. Okay, and we can think what is this, but actually, if we take the Fourier spectrum of this, we see these very narrow peaks that are normal modes of the S. Basically, at these very low frequencies, our data, both direct waves and coda, can be very efficiently represented in the formalism of normal modes, so where the green function is written in this very general form with eigenfrequencies and eigenfunctions of modes. So basically, the non-spherical heterogeneity at these wavelengths and frequencies doesn't play an important role. This is why we can express everything deterministically. And this decay is just coming from the fact that in real equations, we also have attenuation part that I didn't write explicitly here. Basically, all this is a quality factor decay of different modes. Okay, so at very low frequencies, things are simple. Okay, now when we go to very high frequencies, this is another example. So this is one earthquake in Kamchatka. You see time scale is completely different. So this is an earthquake maybe a few hundred, no, less than 100, about 100 kilometers from the station, okay? And we can distinguish P wave, S wave, and everything else is as you see. Okay, and so this high frequency coda is actually, its origin is very different. It's so results from this phenomena of, that again, that we will discuss a lot. In particular, I think Michel Campillo will speak about this, that we call multiple scattering, or superposition of many diffracted or scattered waves. Basically, the idea, we have our earthquakes, our station, we have direct wave that arrives here and here, but then we have many of these heterogeneities, at which of these heterogeneous waves are diffracted, and all this arrives later and builds this coda. Okay, and this is a very complex wave field. So we don't have information about exact information about heterogeneity at this scale. It's very small scale, disorganized. So this is why it's more productive to describe this some random complex media, and describe the corresponding wave field as a random diffuse wave field. Okay, and I think there are different definitions of the diffuse wave fields, and maybe Michel will discuss this. One possible definition is superposition of many randomly arriving plane waves. Another is superposition of random modes. Okay, even I'm not sure if we can reasonably speak about modes in the S at these frequencies, but we can still use this formalism. Okay, and so this diffuse wave field is really what we are very much interested here. Waves in complex media. Okay. So, just a few words. What happens with coda at intermediate periods? So, this is the coda that is shown here. When we don't filter, it's dominated by these frequencies. Obviously, there is a contribution of diffraction and scattering in this coda, but also we can actually, if we look at the seismograms and analyze with different methods, we can recognize in this coda many deterministic arrivals corresponding either to multiple orbit surface waves or to reverberation of body waves. And this is also very interesting problem, how we separate between these two contributions, scattering and deterministic, to this late coda. Okay, so what we will, I think, speak a lot about in the school about this random diffuse wave fields in seismology. If we speak about seismology, there are two candidates. One is coda, that I just briefly presented, that can be idealized with these descriptions, either of sum of random plane waves or sum of randomly excited modes. Another candidate for diffuse wave field is a seismic noise, that is again excited by ambient noise sources mainly acting on the S surface or exclusively acting on the S surface. And this noise is often represented as a wave field excited by this distribution of sources, F, that has these properties that it's incorrelated in space and time. So when we take this correlation, it gets us delta function in space and time. Okay, so okay. Obviously, what is important to always remember, and when we write these representations of these candidates to the fields, diffuse fields, these are mathematical abstractions that can be reasonable, work as a reasonable approximation in some cases, and not good in other cases. And I think this is the main issue of what we are trying to do to advance our methods. Okay, but I start with some very basic thing that we, I think all of us knew now, that we use in seismology and other disciplines for more than 20 years. We call it sometimes as cross-correlation theorem, that is valid for diffuse wave field, that states that this, so if we have a diffuse wave field, sufficiently long records at 2 points, we take the function of cross-correlation, it's a special time derivative, and it converges to this expression, that is combination of two Green function, causal and anti-causal, okay, with some normalization by the noise power. Okay, and so this is a very powerful statement that tells us that if we take cross correlation between two stations, we just eliminate all possible source complexity and we just obtain the wave propagation from one point to another. Okay, basically, if we take our schematic representation, so that our data is somehow convolution of sources with green function, and source can be complex functions that we don't know well. If we assume that our wave field is diffuse, we can replace this cross correlation with green function. Okay, so we eliminate the source complexity, and this is what has been used now in many applications. But before telling about how we use it, I will start with simple illustration. I think this is an illustration that is used in many lectures or presentations, how this works, and I often use it also when I show this to students. So we take our two stations, okay, then many sources surrounding them, and every source emits, and we consider homogeneous 2D media in this case. So every scalar, every source emits some random signal to both of stations, okay? And then we take these records at these 2 points, we compute cross correlation. So if we do it properly, so we write it like this, two wave fields and two stations. So, and then we write explicitly how these two wave fields correspond to sources from different, contribution from different sources. We end up cross correlation described like this, and one of the terms is eliminated because we assume that our sources are uncorrelated, okay, or as we assume it for diffuse wave field. So basically our cross correlation from many sources combined can be computed as just cross correlation, sum of cross correlation from every individual source. And then if we compute cross correlation from every individual source, it's governed by simple geometry. It gives this function. And then when we sum all these, because of this phase, stationary phase contribution from this part and this part, we get these two peaks corresponding to our causal and anti-causal green functions. Okay, so this is a very nice illustration of how this works. But I insist, it's an illustration. It's not actually a demonstration of the full theorem. So the full theorem is not valid only for homogeneous 2D media. It's valid for actually arbitrary, well, not arbitrary, but a very large class of heterogeneous media. There are many papers about this, or at least a few ones that if somebody is interested, I can show some of them later. So when we deal with real situation, our media is not homogeneous 2D, not scalar. Our green function is not a simple pulse in homogeneous media. Actually, when we deal with a real situation, our green functions are like this. They contain all these complex waves, and especially they contain, at some scales and frequencies, they contain this coda, okay, the scattered wave field, or diffracted wave field, multiply scattered wave field. Okay, and this is very important. So because you see, if we compare, for example, in this seismogram, the energy of direct waves and of the coda, they already not very different, and often when we do cross correlations, we normalize the amplitude, so the duration of the coda is much longer, so its contribution to convergence is really important. So this is what we always have to remember, that when we deal with the theorem, it's not the reconstruction, it's not only built from ballistic waves, but in many cases mostly from the coda. So coda is important both for convergence, but also it is in a case of idealized, fully diffuse or random or equipartitioning wave field, it is fully reconstructed. This is the theorem. Okay, so I think this is a very important thing, because I have seen recently that there is not a full understanding of this. Some people think that only ballistic waves have been demonstrated to converge because of these simplified illustrations, but in reality, not. The theorem is valid for the full green function. Okay. The other thing that is if our wave fields are really why I put it here? What I'm doing? Okay, I went here. Okay, I don't know. So, okay. So we will discuss this later. I want just to start with once this statement or its applicability to real seismic data, to first to the coda and then to the noise was demonstrated in 2003 and 2004. It immediately started to be used, and I mean especially it's very interesting with our modern networks because what we can do with these cross correlations, use them as virtual seismograms. When one station is a source, virtual source, all other stations are receivers, and ideal number of these seismograms grows as n square of number of our stations, and with large networks, this gives us a tremendous amount of data to deal with. And so, what is going on? Okay, there are many applications that have been done. So the synthesis of virtual seismograms, and once we have them, we can immediately just take the methods that has been applied to earthquake records and use it with these new virtual seismograms. So, for example, we can do surface wave tomography, and there will be presentation more detailed about noise-based surface wave tomography by Ann Paul. So we also have some cases where we can extract body waves. It's more challenging, and there will be presentation about this. And then we have this monitoring, and also another interesting application that has been suggested also some time ago. It's that we can use actually this virtual seismogram as some proxy for ground motion during future earthquakes in places where we don't have records of this earthquake. So it also has some possible implications for evaluation of seismic hazard, and I think or ground motion during future earthquake. And Fabrice Coton will speak about this. Okay, and just I will show you briefly some. How much time do I have? Okay, I think I can do this. I will show briefly some well-known examples. So this is, I think, one of the first publications when we demonstrated that when we take noise, we extract this nearly symmetrical, at least in time, cross-correlation function. And it has been recognized that these waves are Rayleigh waves, and then it can be used for many purposes. For example, this is a illustration that I like very much from Fancellin when he took the US array. At this time, he took one receiver as a virtual source, cross-correlation with all other receivers, and so he reconstructed this virtual wave field, again composed of Rayleigh waves, that propagates this from this virtual source to all other places. You can see that this is the position of virtual wavefront at 100 seconds, and this is its position at 200 seconds. And what is interesting, it really follows the propagation in the real S, because you can see, for example, here the wave in this part, the speed of propagation or times are later than in this part, because on coastal part of the US there are all these sedimentary basins, and so this was a very nice result, and it has been used for surface wave tomography, like for example this one with US array. I think based on this approach, the tomography of the crust and uppermost mantle in many places where this dense network was largely improved. Okay, and again we will see this for Europe, I think, in more details. Okay, so then another family of applications is this noise-based monitoring. The idea very simple. So if we believe that we reconstruct the Green's function from the noise cross-correlation, we can do it if we have two stations operating for long enough, many times, repeatedly. And so if there is some changes in the media, it will affect our Green function, and we can retrieve it from our correlation function. And again, one of first example was by Florent when this was applied to Piton de la Fournaise volcano in La Réunion Island. And it shows these repeated cross correlations computed in different windows. And when we look at them like this, we cannot actually see much difference. But then if we apply advanced, appropriate methods of travel time shift measurements in the coda, this is very important. Actually, we don't rely on ballistic waves. You see, they excluded from here. We mostly rely on the coda. Okay. And we retrieve this time shift that can then be interpreted as the tiny variations on velocity of the media. It has been shown that volcano is inflating before eruptions. Okay. Another application from, I think it's from Main's group, was done to use the same technique to monitor changes in a sedimentary basin related to hydrological properties, hydrological processes and changes. And there will be a more detailed presentation of this from Shijuan. So this was very successful. Okay. So as I told, we have now plenty of applications that have been built on this hypothesis that cross correlations are equivalent to Green's function. But actually, we should ask a question, is it really working for real wave fields in the S? And we know the answer, that is, it's not working. There are many reasons to understand this. First of all, for example, for the noise being random and diffuse, we need seismic sources everywhere. Okay. And for example, we don't have noise sources at depth. All noise sources are acting on the S surface. Also, if we take even earthquakes occur up to depths of 600 kilometers. There is no earthquakes in the most of the S volume. So we cannot have a fully random and diffuse wave field for all waves. Maybe for surface waves. Okay, but again, we need to check this out, and this has been done. Basically, we use for this, we used the property, very simple, that if we have fully diffuse wave field, here it's schematically represented by these sources acting everywhere, our cross correlation is expected to be fully symmetric. Okay, but then if we have situations when there are some heterogeneity in source distribution, we will not retrieve the same energy on both sides as it's shown here. And we started to look at our real cross correlations. For example, here in California, this is in the period of secondary microseisms. This is in the period of primary microseisms. And we can see that they are never symmetric, almost never. So the zero is here. In this case, it's completely one-sided, actually reflecting the fact that the most of seismic noise is generated on the oceanic side. Here, at longer periods, it's more, it sees not only in the closest ocean, but more broader region. But again, it's almost always asymmetric. Okay, so this is how we very quickly have seen that actually noise sources, they are not located homogeneously everywhere. They are mostly in the, well, I mean, at least at these frequencies, mostly in the oceans, and again in some particular spots in the oceans corresponding to strong storms, waves, and so on. And there will be a presentation about this by Fabrice Ardouin, who is not here, but I think he will speak about the physics of generation of noise by the oceans. Okay, so basically what we now we know this quite well. If we speak about seismic source distribution in general, as I already told, ambient noise sources, they are at the surface. They are only, I mean, if we speak about microseismic noise, obviously if we speak about high frequency noise, it can be very different. By microseismic noise that we use in many applications, it is originating in specific oceanic areas, and actually very few body waves are generated, mostly surface waves. Okay, for earthquakes, again, they are relatively shallow, corresponding to the S side, and they are located again in some specific alignments, not everywhere. So our wave fields in seismology are never homogeneously diffused wave field. Okay, so we use these approximations often, and I think in many cases it's validated, but we need always to be careful about this. Okay, so cross correlations converge to Green's function only partially. For example, I think we know that at some frequencies and cases, surface waves are well reconstructed. When we speak about body waves, it's much more problematic. Okay, and so then for some contributions, we can actually ignore this. For example, if we use travel times of surface wave for tomography, it's okay, especially if we think that at frequencies that we use, apart the noise distribution, when we do reconstruction of Green function, there is also a contribution from this scattering on S heterogeneity. So we reconstruct, in many cases, surface wave well enough to measure their travel times. Then if we speak about, for example, monitoring applications, okay, in many cases, we can do it as we do it today without thinking too heavy about noise sources. Because of two reasons. One is because we use the measurement from the coda, not from ballistic waves. Okay, and this is physically very important. And then it has been demonstrated, I think, I don't know, Michel, if you speak about this, that in when we do measurements from the coda, they are less sensitive to direct source position. They are much more stable, again, if there is some stability in noise sources. Okay, but then, obviously, there are other class of applications where we can ignore this, okay? Where we can actually go back to our original equation of cross-correlation to write the full wave field and to end up with something like this. When our cross-correlation is actually not a Green function, but a convolution of two Green functions with this multiplied by this source density that depends on, in this case, on frequency and on space. Okay, and there are, I just show some cases where this might be important. For example, this very long period seismic hum. Okay, if we don't to use it. As I have shown, at this scale, there is no lateral heterogeneity, significantly affecting our waves. And so, this is the study from Laura Ermert, where she's shown that the sources are distributed really inhomogeneously. So if we want to do accurate things with this wave field, we actually need to account for noise sources. I think the same thing applies to many situations where we work in environments with human activities. We have dominated sources from some particular hotspots related to trains, cities, whatever. Okay. Another case where direct application of cross-correlation theorem is partially problematic is body waves. Okay, I think many of you have seen this figure on Pierre's paper, where this is the global cross-correlation from the global network at this time. Okay, and we can recognize in this time-distance plot, again, our Rayleigh wave, but also some P waves, so again, some waves that corresponds to well-known arrivals. So we retrieve some body waves, but also we see some arrivals that are not physical because it's vertical to vertical. And since then, the research on this wave field and its possible use for imaging deep S continuous. And I think it has been recognized that some of these contributions are not due to seismic noise, but to coda of large earthquakes. But then there was a suggestion that if we know reasonably well the noise sources, we can also use information about their location to find good configurations to retrieve some travel time information from these waves. Okay, there will be a presentation about this and a poster, I think, yes? Okay. Okay, and then another configuration where this cross-correlation principle in terms of Green function doesn't work at all are volcanoes. If we have active volcanoes with active tremors, when we do cross-correlation, they are all emitted by very localized source that correspond to volcano and activity. If we try to use this screen function for whatever kind of imaging and monitoring, we will get very crazy results. Okay, so I think it's over. This is what I wanted to show you. Basically that we have this green function in the real S that we try to reconstruct with this cross correlation and different things, but then we have this question about approximations we use and hypotheses and so on. Thank you. Please, questions.